Welcome back, everyone. Let's go ahead and go through the solutions for the Support Vector Machines project. I'm going to head over to the exercise notebook. Okay, here I am at the exercise notebook. We're going to go ahead and scroll down to our first task, which under project goals, if we keep going down, we have complete the tasks in bold. We're going to go ahead and import these cells and run these two cells so we can read in this _fraud.csv file. You'll notice it has a wide variety of chemical analysis features, and then it also has this quality column, which is the label we'll eventually realize, and then it also has this red or white type of wine column. So what are the unique variables in the target column? This should answer the question if this is a binary classification or multi-class classification. All we need to say is grab that quality column and then call unique off of it from the Pandas section of the course, and we know that the unique elements are either legit or fraud. And luckily for us, scikit-learn is quite flexible in whether your labels are strings or numerics. Next, we want to create a count plot that displays the count per category of legit versus fraud, and then is the label or target balanced or unbalanced or imbalanced. What we're going to say here is simply perform a count plot where x is equal to quality, and then the data is df. So if you run that, you'll notice we have way less instances of fraud than we have for legit. And in fact, we can get a count on this by saying something like df quality and then calling value underscore counts. And this will actually report back the counts. So there's over 6,000 legitimate wines in this data set and less than 250 fraudulent. So a bit imbalanced here. Next task is to find out if there's a difference between red and white wine when it comes to fraud, and to do this with a count plot. So the count plot should look something like this. So one way to do this is to just come back up here, copy the SNS count plot, and simply add a hue parameter. So we can say hue is equal to the type. So run that, and this will show us the type and then legit versus fraud. Or what you can also do is switch these and have the hue be the quality and X be the type. Technically, you're still showing the same information. It's just one ratio is kind of more extreme than the other. It's up to you which one is more representative of the data. Here we can see that the ratio of fraudulent to legitimate wines seems to be roughly the same for red and white, but we can go ahead and calculate this with a percentage, which is what the next task asks us to do, which is what percentage of red wines are fraud, what percentage of white wines are fraud. To do this, let's go ahead and separate out reds versus whites. We'll say reds is equal to the data frame, where data frame type is equal to red. Then we'll also do the same thing for whites, where df of type is equal to white. And then we simply need to calculate the percentage. So for that, we want to first figure out the fraudulence occurring in white. So we can say reds where quality is equal to fraud. And then from that, we're going to say, go ahead and give me back reds where reds quality is fraud. So if I run just this cell, this returns back all the red wines that happen to be fraudulent. However, I actually want to know the length of this. So how many were there here? There's 63 fraudulent red wines, and I want to divide this by the length of the total number of red wines. And in theory, you could do this as one giant long one-liner in Pandas, but it's a little easier to understand if you break it up into steps. So then we going to go ahead and multiply this by 100, and that gives you the answer of 3.9399%. And for the white wines, it's the exact same code, except you replace reds with whites. So go ahead and calculate the fraudulent whites, the number of those, and then divide it by whites. So you can see here, more or less, there's not going to be a big indicator of red versus white for something being fraudulent. They're pretty much the same percentage of fraudulent wines, whether you're looking at just reds or just whites. Next, we want to calculate the correlation between the various features and the quality column. Recall that the quality column is actually still a string, fraud, or legit. So in order to calculate a correlation, that is a numeric Pearson correlation between the quality column and the various features, we do need to map some sort of 0 or 1 to a new feature. So we'll go ahead and say df and create a new column called fraud. And this column will essentially be the quality column, and it's going to be a 0 if it's legitimate or a 1 if it's fraudulent. So say df quality, go ahead and map, and we're going to say map legit to 0, and then say fraud, map that to 1. So we have that, and then I can say df find the correlation. So this is going to return the correlation between everything, but I'm actually just interested now in this fraud column. And now I can see how correlated things are, that is, the features are, to being fraudulent. Recall, fraudulent is a 1 here. So if something was perfectly fraudulent, we would expect it to be 1-to-1 with fraud. And what I can do here is I can call everything but the fraud column. So notice if I say go from the beginning all the way to -1 index, that's going to remove the fraud column, or I should say fraud row, really. And then we can sort the values, run that. Now that it's sorted, I can plot this using the same code we've seen before. It's kind of Pandas shortcut code to create a bar plot. If you wanted to, you could also do this with Seaborn. We've done this before in various projects already. Okay, so I can see that it looks like acidity is going to be an important feature, as well as free sulfur dioxide. But is there really enough signal here to detect legitimate versus fraud? We'll have to explore that further. Lastly, we want to create a bar plot. And what we're going to do here is create actually a cluster map plot. So cluster map of the correlation. So we'll say df correlation. And the color mapping, we can go ahead and say is Viridis. Make sure that says CMap is equal to. So run that, and we can see this correlation. You can also add annotation or change the sizing, and you can do any other visual exploration you want with this. All right, so what we're going to do here is move on to the machine learning model tasks. Now, before we actually run this machine learning model tasks, we do have to remember to get rid of that fraud column we just made. So before we do anything, I'm going to say df is equal to df drop that fraud column, because I can't have that as a feature because I already have the quality column. And I don't want a perfect 1-to-1 with the label. So again, notice I still have, if I scroll over to the right, the label that I'm trying to predict, legit or fraud. I couldn't have this kind of duplicate in there as I continue on. So my data frame now is ready to go. The first task was to convert the categorical column type from a string red or white to dummy variables. You could use mapping for this, but an easy way to do this is to simply say df type is equal to pd.getDummies on df type, and then we're going to say drop first is equal to true. And the reason I can reset this to a single column is because type is binary. It's only red or white. If it was not binary, I would need to do what we've done in the past, which is essentially get this sub data frame and then concatenate it with the original features. But for this case, because it's red or white, I can essentially reset df type, which is just going to be 0s and 1s. Next, what I want to do is separate out the data into x features and a y target label. So I'm going to say my x features are equal to df, and then we drop the quality column with axes equal to 1, and then y is going to be equal to df quality. The next task was to perform a train test split on the data with a 10% test size. So to do all this, we'll say from scikit-learn.modelSelection import train test split, and then we're going to go ahead and say train test split, shift enter, or shift tab, go ahead and run this here, and then we're going to copy and paste this line. There we go, copy and paste. And then I'm going to say x, y, test size, keep it at 10%, and random state as 101. Okay, so now we did our train test split. Because we're working with support vector machines, we always want to make sure that we're going to scale this data. If you're ever in doubt, go ahead and just scale it. So in this case, we'll say from scikit-learn preprocessing, import the standard scaler, create an instance of the scalar object that we're already familiar with. We'll say scalar is equal to standard scalar, and then create scaled versions of the data. We'll say scaled xtrain is equal to scalar dot fit transform. Only want to fit to the xtrain data, and the scaled xtest data. Scaled xtest is equal to scalar dot, and then we're just going to transform xtest. Perfect. Now we want to create an instance of the support vector machine classifier. And previously we have left this sort of model blank. However, we already know that the classes are imbalanced, and there's going to be an attempt to alleviate this issue. What we wanted you to do was to essentially click the link for the documentation. It should have taken you to SVC, and if you check out the various hyperparameters, you should have noticed one that we didn't really talk about, but would be heavily useful for this particular project, which was the class weight. So then, as you begin to explore this, you scroll down, try to understand what class weight means, and you scroll down, and we have this class weight where it could be a dictionary or balanced. And essentially what this does is all classes, if you say the default none, are supposed to have a weight of 1. However, the balanced mode uses the values of y to automatically adjust weights, and this is the important part, inversely proportional to class frequencies. We already know that there are very few instances of fraud. So what we would like to be done is that the features for fraud are given a little more weight during training. Essentially saying that set the parameter c of that particular class instance to class weight times c. And the weight is going to be determined inversely proportional to the frequency of that class. So what that means is the less times this class happens to show up, the stronger the weight is going to occur for regularizations. So balanced is essentially going to try to auto-balance the classes for you by adding a weight to the instances of the classes that are imbalanced. And it does this through this formula right here. Okay, so we're going to come back here, and we're going to say that from scikit-learn.svm import svc. And then svc is equal to svc class weight, and then we're going to say balanced. So this is what I'm going to work with for my based model. So all my other models will always have class weight is equal to balance. I no longer need to actually prescribe this in the parameter grid. Next, we're going to create a parameter grid. It's really up to you how many parameters you want to search for, what kernels you want to explore. We'll go ahead and say from sklearn.modelSelection import grid search CV, and we'll begin to just make a very basic parameter grid. I won't attempt to solve this to some extreme level because we are just filming the solutions here, but I'll create some C values to check out. We can start them quite low and then kind of logarithmically space them. So 0.01, 0.1, maybe 0.5 and 1. We can try different values of gamma, either scale or auto. You can also try different kernels, up to you. I will just explore, for the case here, different values of C. And you can let me know in the Q&A forum if you were able to get better results than I did here. We'll say grid search CV, SVC, param grid. Run that. It's going to perform a grid search. And you can also test out different gammas like we did here. But we'll say that the grid, check out the best parameters from it. So after you run this, oops, we actually forgot to fit this. So we need to fit this to our scaled xtrain data and then our ytrain. There we go. So that's going to take a little bit of time to run through all those combinations for C, but after that, then you should be able to say grid best param underscore, run that, and it's going to report back the best parameters for that particular model. And it looks like the best parameter it found was C equal to 1, which if you can recall, if you come back here to SVC, C equal to 1 is essentially the default. So it's not doing too much beyond the default. And again, you can always experiment with different kernels, etc. Now let's go ahead and display the confusion matrix to analyze the results. We'll say from sklearn.metrics, import the confusion matrix. I'm also going to import the classification report. get our predictions. We'll say grid predictions is equal to grid.predict scaled x-test. And let's check out the confusion matrix here. So the confusion matrix, y-test, grid preds, run that. You'll notice that it's essentially misclassifying 92 and 10 here. And if you want, you can actually plot this out. So you can also import if you want. Recall we have plot confusion matrix as an option. So plot confusion matrix. And that actually takes in the model itself along with the values. So we can say plot confusion matrix. That's going to take your estimator, your x, and your y true. So that would be your grid. And then x is scaled, x test. And then we're going to have y test. Run that, and that will plot this out. So the reason I show this is because we can compare the true label versus the predicted label. Unfortunately, it looks like for 92 legitimate wines, we thought they were fraudulent. And then for 10 fraudulent wines, we thought they were legit. And we're actually only able to get about 17 of the wines that were actually fraudulent, which means it might be good, because it's an imbalanced data set, to take a look at the full classification report and understand precision and recall. Because really what I want to know is, out of the fraudulent wines, how often am I actually getting those right? To do this, we simply say print the classification report and pass in y-test versus grid predictions. Run that, and you should get these results if you use the same train test split that we did. You'll notice that the precision and recall for fraudulent is actually quite poor. And then you can see the combination between those as the F1 score. Pretty good as far as legitimate wines are concerned, but that's really not the whole purpose of this model. The whole purpose of this model is to hopefully catch these 10 wines right here. And again, you could try performing a wider grid search to see if there's parameters that can help you with that, or you can even try different machine learning models. But at the end of the day, given the variety of models you can try, eventually you should be able to see that this is a very difficult problem to perform chemical analysis and actually predict whether a wine is fraudulent or legitimate. And the main thing behind this is the fact that wines, when it comes down to the actual chemical properties of it, that's really not the differentiator between the fraudulent wine and the legitimate wine. They're essentially just fermented grape juice, and it's very difficult to tell them apart, chemically speaking. So the issue really should be trying to focus on other features beyond a chemical analysis. Things like label analysis, checking where you purchase this from, historical analysis, etc. What really this machine learning model in this project is telling you that while the machine learning model and chemical analysis could be a good first step, really what you should be doing is focusing on expanding your feature set to other areas of your domain expertise and hopefully wine fraud in order to figure out what are better features to look at, because right now your precision and recall values are quite poor when it comes to actually trying to find the fraudulent wine. Okay, so that's it. Hope you enjoyed this project. I'll see you at the next section.